We can start. Yeah. Welcome to the next session. We are going to have two talks about superconductors, learn many different things, magnetism, elasticity, nematicity, everything except superconductivity, as far as I understand.
No, there will be superconductivity.
Okay, very good.
Thank you.
So our first speaker, Rosa Valenti from Frankfurt University. Please.
Thank you very much, and thank you to the organizers for this invitation to come to this really wonderful city. And in this talk, I will discuss the effects of strain in iron-based superconductors and its role on the nematicity, the magnetism, the superconductivity, and also recently observed superelasticity in these materials. First of all, I would like to acknowledge my collaborators in these studies. These are Vladislav Borisov, Stefan Bakas, who were former members in my group and are now in Uppsala and École Polytechnique in Paris. Karin Samtuk, who is a PhD student in Frankfurt, Rafael Fernandez from the University of Minnesota, and the experimental groups from Paul Camfield at Ames, Amalia Koldea, Matthew Watson, and Timur Kim in Oxford and St. Andrews. And I'm going to attack this question of strain effects on all these phases in iron-based superconductors from an ab initio point of view. So in fact, now we are about 11 years since the first discovery of superconductivity in these iron chalcogenides and pnictides. And if we were to put the observed phases of these materials in a generic temperature versus pressure or doping phase diagrams, so what we have been observing is that these systems show, are metals and show a superconducting phase with quite high TC. So the highest TC up to now is 55 in 55 Kelvin in bulk, and one has gone, in fact, also with layers. There was one report of 100K in iron-selenium layers, but this hasn't been confirmed. And there is always a magnetic phase in the vicinity of this superconducting phase, as well as then, it's not very strong, as well as various nematic phases and structural phases. And along the years, one has been observing, in fact, new effects that come into this phase diagram. And today, I would like to, in fact, deal with three new recent observations and predictions and how we understand these observations in terms of ab initio based methods. So the three observations I want to discuss, the first one was done last year, where a new type of nematicity was observed in these materials. In fact, in the so-called extreme hole-dope iron-based superconductors, where the cation in between these iron-arsenic layers are the rare earth alkaline, rubidium, cesium, or potassium. The second case I want to deal with here is also the observation of a new magnetic order, which in fact it's a spin vortex magnetism, as well as superelasticity in the so-called 1144 materials. This is nothing else as 1 to 2 materials where there is an alternation of the cation between rare earth and, between alkaline and alkaline earth cation. And the third part of my talk, I would like to discuss correlations in these materials and, in fact, the effect of non-local correlations. And I will define what we mean here by non-local correlations. We had a very nice talk this morning about correlations. So here I will show what we mean and why they are important for describing the properties of these materials. In fact, I'm going to treat these issues, these properties, by considering a combination of density functional theory, which is very helpful to understand the electronic, magnetic, and structural properties of these materials, and combine them also with many-body methods. So dynamical mean field theory, as well as a new method that we have been working with in order to include non-local correlations in these descriptions. So a good starting point for obtaining information about the electronic and magnetic properties in crystalline materials, in our case, these iron-based superconductors, is to analyze the symmetry. And all these material families of iron-based superconductors in the high temperature phase, they crystallize in a tetragonal symmetry, either in the space group 129 or in the body centered 139. And what I want to do now is to concentrate on two symmetries that are given in these spatial groups. One is the C4 rotation, a rotation in fact, along the C-axis of 90 degrees. And the other one that I want to pay attention to is a glide symmetry. So the glide symmetry is in the plane. So if you put yourself a mirror plane in the iron plane, and then you do a translation, have a unit cell, then you will observe this glide symmetry. So now what I want to do is start by analyzing the magnetism, the possible magnetic states that I can have within this symmetry. In fact, by breaking also some of these elements that I showed to you, either the C4 or the glide symmetry. So the most general way of writing magnetism in the iron lattice, which is a square lattice in these tetragonal symmetries, is by considering, most generally, two propagating wave vectors, which are the pi0 and the 0 pi. I have a square lattice. And I can write then the magnetism as a function of these two propagating wave vectors, where M1 and M2 are magnetic ordering parameters. And depending on this, the value of these magnetic ordering parameters, we can realize different type of magnetism in the system. So the most commonly observed magnetic order in these materials is what we call the stripe order. And the stripe order, in fact, requires the breaking of the C4 symmetry into a C2 symmetry, as well as time reversal symmetry. So the stripe order, if we write it in this expression the general expression of the magnetic order, it corresponds to either setting the M1 to 0 or M2 to 0. And it's striped because it's ferromagnetic in one direction and antiferromagnetic in the perpendicular direction. So it makes stripes that, like in a caterpillar. What is interesting about this stripe order is that it allows, in fact, the existence of nematic phases. And what do we call here nematic phases? These are phases where the rotational symmetry is broken. However, we don't have broken time reversal symmetry. And of course, translation symmetry is also conserved. But the issue is that we don't have a long-range magnetic order. So nematic phase, we can think in this stripe order as having, if you see this darker and this lighter picture, you will see that this stripe order builds two interpenetrating Nel lattices. And basically this nematicity, it means you have fluctuations between these two lattices. Basically these are the fluctuations that you can realize in this state. And the way of mathematically express this nematicity is that the expectation value of your spin is 0 because you don't have long-range order. However, you do have non-zero spin-spin correlation functions. So this, in fact, gets into this. This, in fact, is the order parameter of the stripe order. And there has been a lot of discussion about the origin of this nematicity. This nematicity is, of course, coupled. It couples linearly to the strain. So in this case, we will have some orthorhombic strain because we have these non-equal iron bonds. But the question is, what creates this nematicity? Is this the spin degrees of freedom? Is the orbital degrees of freedom, since these are multi-orbital systems? And there is a lot of papers here. It's just the starting, and there are many, many papers discussing about the origin of this nematicity. So and what I want to now discuss is, in fact, let me show you now the big phase diagram where we see where this nematicity appears and what has been observed last year regarding this type of nematic phases. So here I'm just considering these 1 to 2 materials again. So the 1 to 2s, these are these body-centered systems where we have the iron arsenic planes separated by an alkaline or an alkaline earth cation. And what we knew up to last year is that in all these materials where we have barium or calcium or strontium as cation, so the nominal state in the iron is 3d6, so we have 6 electrons in the iron, and the systems show, in fact, I'm doing here as a function of the doping, show an antiferromagnetic stripe phase. Then the system gets superconductor by changing the doping, and there is this region near the stripe phase of nematicity, of this state where the C4 symmetry is broken, but there is no long-range antiferromagnetic ordering. Now, by changing the doping in these systems, basically by exchanging the cation, which we go from a 2+ to a 1+, there is a region, so this stripe antiferromagnetism disappears. There is a region of superconductivity where it is highest at DC. And then going into these materials where we have either rubidium or cesium or potassium, what happens is that the systems remain paramagnetic in the tetragonal phase. There is no structural distortion. And at low temperatures, they superconduct. And what was recently observed is, in fact, that the systems show nematicity and nematic order, which is not the nematic order that I was just presenting to you, considering these two interpenetrating Néel lattices. And the question is, why is this happening? What is the origin of changing this nematicity? Here we don't have a reference antiferromagnetic order to understand where these nematic fluctuations could come from. And this is here, in fact, the experiment, just to show you that, since the title of my talk is strain effects, that this nematic behavior is always observed when you strain the sample. So here, the experiments that have been done by Ishida and collaborators is the following. So these are elastoresistance measurements. So what you do is you measure the variation of the resistivity in the system when you apply an external strain, which is controlled by a piezoelectric device. So now, depending on how you're applying this strain, whether you apply it along the iron-iron distance or the iron-iron distance, or along the 110 or along the 100, you get different behavior of the nematicity. So here, as a function of temperature, whether you have the barium system or whether you have the rubidium system. So you see there is a switch of nematicity character by going from one system to the other. And the question is, where does this come from? So what we did is, in fact, if we want to analyze that from an ab initio point of view, where in principle we have all the ingredients that play a role in this magnetism, of course, in DFT you cannot describe fluctuations. However, what we can analyze is which are the underlying magnetic orders that may play a role for the appearance of these kind of nematic states. And in fact, here is the stripe order that we were talking about, and the corresponding nematicity, which is this B2G, is the nematicity that we knew up to now, which in fact it's present in most of the iron-based superconductors. So if we were to now look which is the underlying magnetic order that corresponds to this B1G nematicity, this new nematicity, this would correspond to what we call the double stripe. So the idea is now to analyze, so since the EFT is a variational method, so let's analyze in which magnetic state this system, in fact, is most stable. And this is what we did. So basically, we did simulations with different magnetic states by considering the end cases is by having the extreme hole dope case, so the rubidium, iron 2, arsenic 2, and the starting point is either calcium or strontium or barium 1 to 2. And now what we do is we do simulations either by doing supercell calculations or by applying the virtual crystal approximation in order to get an information about the magnetism along the way between this system and these systems, where what you change is the electron counting, because here you go from iron 3d6 to iron 3d5.5, as well as when you substitute, in fact, for instance, strontium or barium by potassium, potassium is, or rubidium is much larger, therefore you are also doing some straining to your lattice. So we have to take all these terms into account, all these effects, and see what is the, in fact, what is playing the strongest role into having this change of nematicity and what it's related to the underlying magnetic order. And in fact, that's what we see. So here I'm showing the difference in energies between the single stripe order and the double stripe order, which would be the parent state of the new nematicity. So that means that blue, it means that we are in the case of single stripe, and red, we are in the case where the double stripe wins. And this is what we observe. These materials, in fact, are stabilized by double stripe magnetism and not single stripe. And in between, we see that the strain, in fact, when you are straining the sample, then it starts, so there are regions in between where you cannot decide whether this is, it's not, in fact, the most important ingredient, while changing of number of electrons that are doing the conduction in this system is fundamental to change, in fact, this magnetism. So, so with that, our proposal is that what we are doing, what happens in these materials is that by doing this doping, you are changing the electron count, and this is affecting strongly, in fact, the underlying magnetism. So that, and this is responsible then for these nematic fluctuations. And right now, so the people are doing now neutron scattering experiments in order to try to investigate this type of fluctuations and state that you should obtain through this order. So this was all related to this symmetry, to C4 to C2 symmetry. But now let's go and look again back to our magnetic state and what other types of magnetism could I expect in these materials starting from the tetragonal phase where they are. So now, of course, I could think of breaking glide symmetry, but still preserving rotational C4 symmetry. In this case, I have various types of magnetic orders that can appear. One of them is, for instance, if the order parameters M1 and M2 are perpendicular to each other, I should realize, for instance, a spin vortex crystal. These are two types, either all in or out, the magnetic moments, or basically two in, two out. So this is a possibility of magnetism that up to 2 years ago had not been observed in these materials. However, in 2016, the group in Japan, IO and collaborators, they were able to synthesize what we call the 1144 materials, which what you do is you take, in fact, and intercalate these iron arsenic plates alternatively by, for instance, potassium and calcium. So by a cation which is 1 plus and a cation which is 2 plus. And they were able to synthesize this perfect intercalation. When you do that, of course, automatically you are breaking the glide symmetry that you had originally in the system if you would have all these atoms to be the same. Now, what do we know about this system? So these systems are, in fact, they don't show any structural phase transition, and they become superconductors at quite high temperature at 35 Kelvin. And the group of Paul Camfield, they did pressure experiments on this material. And what you observe is, here is where we are in the parent compound, in superconducts. Now you apply pressure, superconductivity starts to the TC goes down. And at about 4 gigapascals, there is a drastic disappearance of the superconductivity, as well as there is what we call a tetragonal collapse of your lattice. So the system remains tetragonal, but there is a strong collapse of the C-axis with respect to the A-axis. And the question is, where does that come from, and how can we understand this phase diagram? So we did simulations for this phase diagram, and so ab initio simulation. So basically, we simulate the effects of pressure, we relax the structures, and then we look how the lattice parameters and the position of the atoms evolve as a function of pressure. And in fact, we could reproduce this effect that you have this phase transition, in the sense you go from the tetragonal to the collapsed tetragonal very well, but you can only reproduce that if you include magnetism, the magnetism in your ions. Now, this system, as I'm saying, this doesn't show long-range magnetic order. On the other hand, in DFT, magnetism, we need to include a long-range order. So what we did is we included this information of having a magnetic moment in terms of what we call frozen magnetic order. So we assume magnetic order and then do the relaxations. And of course, what magnetic orders that are in fact compatible with the tetragonal phase, you can have many. You can have a checkerboard or spin charge density wave, or you can have the spin vortex crystal type of order. And what we found out is only by assuming this type of underlying magnetic order, we could reproduce this behavior of the lattice as a function of pressure. And I remember that we were saying that to Paul, and said, look, we have to introduce this type of order, so that means the system should have this type of spin fluctuations. And in fact, later on, with NMR, they could see these spin fluctuations. And moreover, by electron doping the system, they even could realize the state. So if you electron dope this system, then the state becomes stable, and you get this type of spin vortex crystal, which has very interesting topological properties. But let me go back now, what is happening. So we need magnetism. We see that there's a strong magnetoelastic coupling in the system, but what is happening at the phase transition? And at the phase transition, what is happening is very nice chemistry. So the following. So we have in this material, if you see the arsenic atoms, in this symmetry, the PZ arsenic face each other. So when you press the system, what happens is that you are approaching this PZ of the arsenic, and at a critical pressure, but basically what you are doing is a bonding-antibonding type of phase transition. And this is exactly what is happening here. These are the simulations, you go on pressing, and at about 4 gigapascals, you get this bonding-antibonding phase transition. So there is a reduction of the C-axis with a small expansion of the A-axis. And in fact, in these materials, you do have two transitions, because the size of the potassium is much larger than the size of the calcium. So therefore, if you go on pressing the sample, then at about 12 gigapascals, you get the collapse in the second layer. And this is now a system where we call it has two half-collapse phase transition. But what is even more interesting is that now in the group of Lee, what they did together with Paul Camfield, they basically, out of the single crystals, they cut these nanopillars, and they applied now strain, so basically uniaxial strain. So they make basically a uniaxial strain along the C direction in this system, and of course this is going to be very effective to reach this half-collapse collapse phases. But what was interesting is that the systems show, so this is the curve of stress versus strain, going up to, in fact, of the order of 17% strain. When you go out, 5 minutes, when you leave out the pressing, then the system recovers almost without losses, again, the initial form. And this recovery, in fact, is extremely important because you can use this material, and we call it superelastic in the sense that you have almost no losses along this phase of going and doing the strain back and forth. And in fact, it has a recoverable strain which is much larger than the best known shape memory alloys. So you can use now, because through this transition, you go from a superconducting to a metal phase, you can use this as mechanical switch between superconductivity and metallic state. So I have 3 minutes, I guess, for the non-local correlations, 4, 5, thank you, 5 minutes. So let me go to the non-local correlations. And first of all, let me go to the correlations. So here I'm talking in the language of Green's functions. And the way so what do we mean by correlations is if we have a system which is non-interacting, and here what I'm drawing is the spectral function, so basically what you measure in ARPES experiments. So basically in a non-interacting system, you are having that you are going to have delta functions, so your quasi-particles live forever in principle if you are in an ideal case of non-interacting, because there are no interactions. As soon as you switch on interactions, and in this case I'm talking about electron-electron interactions, so you are going to have certain lifetime of your quasi-particles and also some transfer, of course, of a spectral weight between your quasi-particle peak and then what we call the Hubbard bands. So, and we can express these features in terms of self-energies. So it contains the information of the electronic correlations, electronic interactions in your system. Now, a method that has been rather successful to describe these features is dynamical mean field theory. But let me show first where in the experiments do we see traces of this correlation, especially in the iron-based superconductors. So, of course, correlation, what it's going to do is it's renormalizing the bands, since we are having now that the bandwidths get reduced since our electrons, due to the strong Coulomb-Coulomb repulsions, are more localized. And therefore, in ARPES experiments, you do see, so here I'm showing for lithium iron arsenic, the Fermi surface, which basically consists of hole pockets at the gamma point and electron pockets at the M point. If you compare the LDA calculations, or GGA, with the measurements, you will see that the measurements show a strong shrinking of this inner hole pocket, which is not reproduced in an LDA or GGA calculation. There are many other measurements where you see these effects of correlations, but let me concentrate on ARPES. And as I was mentioning to you, dynamical mean field theory has been very successful in describing a few of these features that I was just mentioning. So like this renormalization of the bands, and the idea of dynamical mean field theory is that basically you map your system of interacting particles into a system where you have a central particle interacting with the bath. But this interaction is dynamically. So that means that you are describing exactly all local correlation effects. So, and for instance, with, if you can combine LDA plus the MFT, here I'm showing the comparison. You see indeed this effect that by introducing these correlations within this description and taking care of what we call the double counting effects, you do see these shrinkings of the inner hole pocket. And what is important is that there is an orbital selective correlations that is very well taken into account. But you see still there is not a very good agreement with the experiment. And moreover, there is another issue in the experiments that DMFT is not able per construction to reproduce. And this is the fact that in what the experimentalists call the blue-red shift, so that you have, in fact, a k-dependence of these correlations effects. So at the gamma point, your whole pockets get shrink in the down direction, while your electron pockets at the endpoint get shifted in the other direction. And for that, you need to have information of correlations that are k-dependent. So therefore, we decided to generalize to the multi-orbital case the two-particle self-consistent method, which is a conserving approximation, and it's not a perturbative theory. So basically what you do there, you approximate your 4-point irreducible vertex by effective charge and spin vertices, and you determine them by fulfilling some rules. And with this approximation, indeed, this is the LDA Fermi surface, and this is by combining with this TPSC, you see that we can reproduce perfectly. And now you will say you don't, because this is only one-directional. The reason for that is because the experiment is done at the gamma point, and because of matrix elements, they cannot see the other one. But there are, if you go away from this high symmetry gamma point, indeed, it's a flower. So the Fermi surface at the gamma point, at this whole pockets are a flower. And we can reproduce that with this type of calculations. And moreover, if we average over the k-dependence, then we go back to the DMFT results. And here is my last slide. Indeed, now what we observe is you need to introduce this k-dependent behavior, because you are, what happens is that the self-energy has different, is acquiring different sign at the gamma point and at the end point, and this is what it causes this red-blue shift. So basically the message here is that non-local correlations, as I'm defining here, so k-dependent correlations, are important to describe the physics of these systems. And there's recently a paper by Peter Herschel and collaborators where they also show that the superconductivity is important. And here's my summary of the three cases, and I thank you very much for your attention.
Thank you very much. Thank you very much for a very interesting presentation. Now, session is open for questions.
So maybe I missed that, but basically on the first part of the talk is the message that you could actually tune nematicity from one phase to the other using strain?
Yes, in fact, exactly. You can tune it, and in fact the experiments, show, so you can tune, you go from this, so you're asking the calculation or the observation? Okay, so the observation is indeed that they have done experiments on various doping samples, and you go from this nematic, this B2G, to the B1G, but by a region where, so this nematic is what we call an Ising nematicity, basically, because it's a two, basically plus minus. So there is a region where it's not anymore Ising, so that when you are transforming from this B1G to this B2G by just applying the doping. The way we did that in the simulations, either you have to do very big supercells, or you apply this virtual crystal approximation where you substitute, not taking into account the doping, you substitute your atoms by an artificial atom that has the doping that you want. So this is the
More questions?
I was wondering if spin orbit is included in the calculation, and if it's any relevant, if it can change things.
Orbit is relevant here, definitely, in this spin vortex, in the spin vortex state. Here you have to work with spin or orbit coupling, and it's important. And in fact, spin-orbit coupling is important in these materials, especially in, as we know, in the regions where you have band crossings, and we have to investigate that, but spin-orbit is important, even though it's a 3D system. But for this kind of states, you do have spin-orbit. Yeah.
Thanks.
Do we have more questions? Oh. Okay, I have one very simple. You said nematic order doesn't break the time reversal symmetry, but in your actual calculations, you have a magnetic order, right? When you do it in DFT.
Exactly, good point. So the point is, I cannot simulate nematic order. However, what I'm trying to find out is whether the magnetic order that would condense, if you want to call it, which should be related to this nematic order, whether the system shows the tendency to have this order. Because with DFT, I can only consider long-range order. The same way as for the nematic order, the first nematic order, the stripe, the long-range order when you break time reversal symmetry is a stripe. For this other nematic order, this diagonal one, when you break time reversal symmetry, you should go into a double stripe state. And what I'm showing is that the double stripe state is the stable state in this material, more than the stripe state. So therefore, if you create nematicity by introducing fluctuations, you should go into this diagonal type of nematicity. You can never get this diagonal type of nematicity from a stripe ordered state. You have to have a double stripe ordered state. So my point was, these systems, if I analyze if they were to order, which would be the order that they would show? And this is the double stripe. So what kind of nematic fluctuations this double stripe has? These are these diagonal fluctuations. Thank you.
Okay, thank you very much. More questions? So then let's thank speaker again. And our next speaker, Antje Botana.
Sí, no sé si se ha apagado o qué. Está aquí ahorita en la mano. A mutar, vale. Es que no enchute más patear. ¿Vale? Sí. ¿Me ayudas?
Está bien, yo creo.
¿Es bien?
Cae, no se cae. Sí.
Vale, y esto luego te lo enganchas donde puedas.
Sí. Right. Yeah, so I would obviously like to start, like everybody else, by thanking the organizers for the invitation to this wonderful workshop. And my goal today will be to show you that low valence layer nickelates, and I'll show you what I mean by that in a second, might be one of the closest cuprate analogs that we have to date. So I will continue a little bit the line of the previous talk in that I would like to show you how electronic structure methods and more specifically density functional theory can be useful in addressing a problem like this. I won't get to the DMFT part today in my talk. And I'll also show you how doing this you can actually understand and even guide the experiment sometimes as well. Now, before I do all of that, I would like to start by thanking the people that were involved in all or part of the work that I'll show you today. These are Warren Pickett at UC Davis, Mike Norman, John Mitchell, and John Freeland at Argonne National Lab, Victor Pardo at the University of Santiago de Compostela, and Julia Mandi at Harvard, as well as my own group at Arizona State, where I moved a little over a year ago now, but where I already have the privilege of working with a group of very talented people that are working really hard on this problem. Okay, so I'll start from the very beginning, literally. As probably many of you or all of you know very well, the discovery of unconventional superconductivity in cuprates motivated the study of materials that have a similar crystal and electronic structure. And these are what I will call key ingredients of the cuprates today. So in cuprates, first of all, we always have a layer structure to begin with that is based on these copper-oxygen 2 planes. And here you have an example of such a plane, where in blue you can see the coppers and in red the oxygens. So each copper has a square planar environment of oxygens in this structure. In addition to that, in the parent compounds, the copper is always in a 2+ D9 configuration, which leaves us with a spin 1/2 system with strong antiferromagnetic correlations and the involvement of a single band of the x² minus y² character around the Fermi level. And that it's easy to see in this sketch here, where I'm showing the filling of D levels for a D9 ion in a square planar environment, where you see that you end up having just a single hole in this uppermost dx² minus y² orbital. Last but not least, in cuprates, there is also a very strong degree of oxygen P and copper D hybridization. And you can see that easily in this cartoon, where the lobes of the dx² minus y² orbital in red are directed towards the p orbitals of the neighboring oxygen ions. Okay. In addition to all of these key ingredients, we also know that cuprates follow a pretty general phase diagram that now may look familiar because you saw something very similar in the previous talk. So here, once again, in the y-axis, we have temperature. In the x-axis, we have hole doping, or a change in the chemical makeup of the material. So we always start in this corner of the phase diagram at D9 filling, for which we have an antiferromagnetic MOT insulator. Now we start doping the material. At some point, superconductivity appears. Keep on doping further, reach a maximum in Tc in this dome, and keep on doping even further, and at some point, superconductivity just goes away, and we enter what it's called the overdope regime, where we should be finding a metal. That's, of course, a simplified view. This phase diagram is way more complicated. There are plenty of other phases here. But the main point that I want to make with this is that we do know, of course, a lot of things about the cuprates. However, in spite of having good ideals, perhaps too many ideals, about the mechanism of high-temperature superconductivity, there is no quantitative theory yet. So finding cuprate analogs has been perceived as a plausible strategy that can help you in trying to elucidate the origin of high Tc and eventually perhaps even help us design superconducting materials with higher critical temperatures. At least that's the hope. Now, of course, looking at possible analogs to the cuprates is not something new. It's not that we are the first ones coming up with this idea. People have looked at quite a few different ones throughout the years in hopes that superconductivity might emerge. Would say no, not with a lot of success, probably. Now, in this regard, nickelates have been around for a while, and the reason for that is very simple. If you go back to the periodic table, you instantly see that nickel and copper are by one another in it. Also, nickel 1+ is actually isoelectronic with copper 2+. So the thought is, okay, if I'm able to stabilize a material in which I have nickel 1+, maybe I have a good starting point. In terms of nickelates as cuprate analogs, people have looked at quite a few different ones throughout the years, but the ones that we decided to focus on more or less 3 years ago now are what I call low valence layer nickelates. And these are materials that belong to a series, and all of them have infinite nickel-oxygen 2 planes in analogy to the copper-oxygen 2 planes of the cuprates that I showed you in the beginning. This is their general formula here, where R, it's a rare earth that can be lanthanum, praseodymium, or neodymium. And this N factor that you see over here determines how many nickel-oxygen 2 planes you have along the z-axis. So basically, for N equals 2, you will have the bilayer material. For N equals 3, the trilayer material, and so on and so forth. Now, one thing of these systems, though, is that they are not synthesized directly in this layered form that you see here, but they are obtained by oxygen reduction from parent phases that preserve the apical oxygens. And I'll show you an example of that in a second. But already from this cartoon, it's kind of easy to see that these systems are very similar to cuprates in terms of their structure, at least. And I'll show you also in a second that they are also very close to cuprates in terms of electron count. Now, as much as I like the physics of these materials that, as I said, I've been looking at for 3 years now, Up to 4 months ago, I would have had to tell you, well, I think they are really interesting, but they are not superconducting. But 4 months ago, things changed quite dramatically with the first report of superconductivity in a nickel oxide material. More specifically, on hole-doped neodymium nickel oxygen 2, that it's an infinite layer member of the series that I just showed you. So, of course, I will like to tell you today a little bit about these infinite layer compounds, or R nickel oxygen 2 materials, or 112 materials, if you like, for simplicity. This is how their structure looks like. You see that we have adjacent nickel oxygen 2 planes that are separated by a single layer of the rare earth atom, that is this gray guy that you see here. If you do a simple ionic count, R is a 3+ ion, oxygen is 2-. What you end up getting, it's a nickel 1+, but it's a D9 ion, and if you remember, this is a pseudo copper 2+, if you want. Now, as I also mentioned before, these phases are not directly synthesized in this layer form, but obtained via oxygen reduction from a parent phase that has apical oxygens. And for the 112 material, the parent phase is the perovskite phase, or the 113 phase. So I'll tell you about the infinite layer compounds, but the other members of the series that I wanted to tell you about, because these are the ones that we have been looking at for a while now, are the tri-layer members of this series. So if you do simple math here for n equals 3, this is what you end up getting, R4 nickel 3, oxygen 8, or R438 for simplicity. This is how the structure of the tri-layer material looks like. You see that we have 3 nickel oxygen 2 planes that look very similar to what I showed you before. But now each of these tri-layer blocks, it's separated from the next one along the z-axis by a fluoride slab that it's formed by the rare earth and oxygen. If we repeat our simple ionic count, what you end up getting here, it's an average nickel valence of 1.33+, or 8.67 d electrons per nickel on average. Once again, you don't synthesize directly this material, but you get there by oxygen reduction from a parent phase that has apical oxygens, and in this case, that's the 4,3,10 phase. Now, the main message to get from here, though, is that both the 438 and the 112 compounds have a layer structure to begin with a square planar environment for the nickel, and that they are precisely at or very close to D9 filling. And if you remember, these were my first 2 key ingredients. One can actually try to directly translate these 2 fillings back into the cuprate phase diagram. And if you do that, the 112 materials will fall out here at the corner of the phase diagram, where you would be expecting an antiferromagnetic MOT insulator. The 438 materials will fall out here, well into the overdoped regime, where you should be finding a metal. And we'll see if that's what we find. So now that I've introduced you a little bit to the basics of these layered nickelates, let me then tell you the first part of the story, that is what I now call the story of hope, and that's the story of the 438 materials. So as I said in the previous slide, the 438, in terms of filling, will fall out here, well into the overdoped regime of cuprates, where we should be finding a metal in principle. Now, is that what you find? Well, the answer is no. What you see here are resistivity versus temperature experiments for lanthanum 438 that was already synthesized back in 2009, and you can definitely see that that's not the temperature dependence of a metal. The material is actually highly insulating, up to 105 Kelvin, when a transition occurs towards more of a semi-conducting-like regime. So definitely not a metal. So you start on the wrong foot. You found a material that has a layer structure, that it's close to D9 filling, but that unfortunately is not metallic at 1/3 hole doping. So too bad. But you might just take the challenge as an opportunity and think, okay, is there a way in which I can get a metallic phase from here? And is there a way in which I can actually predict that from first principles? And one thing that you may think of doing is substituting lanthanum by a smaller ion, like praseodymium, increase the bandwidth and hence the tendency towards metallicity and see what happens. So once again, for the 438 materials, what we have is an average nickel valence of 1.33 plus, and this corresponds to a D867 ion. So for such an ion, you can in principle have two different spin states. You can have a high spin state, and that's what is shown on the left. In this case, the states around the Fermi level that are marked by this gray arrow here are DC square in character, and this state is actually insulating because the DC square states are bonding, anti-bonding split around the Fermi level, and that allows you to open up a gap. So if you like, this state is not very cuprate-like. But you can also have a low spin state, and that's what is shown on the right. And in that situation, the states that you have around the Fermi level are dx squared minus y squared in character, and this state is actually metallic. You have a 2/3 field, dx squared minus y squared bond. So already easily from first principles, you can find that the praseodymium material actually prefers a low spin state for its nickel ions. In that situation, this is the type of orbital resolved density of states that you end up getting for the material, in which you have just a wide dx squared minus y squared band crossing the Fermi level, giving rise to metallicity, while you are actually able to have a relatively high degree of PD hybridization, and the oxygen P states are shown here in blue. Now, if that doesn't make you happy, and if you have ever seen a cuprate bond structure, you will instantly recognize this one as such. This is the bond structure for praseodymium 438, in which we have just a single dx squared minus y squared bond crossing the Fermi energy per nickel. So you have 3 nickels, that's why you have 3 bonds. Now, of course, that's just what the theory tells you. Is this what you find in the experiment? And the answer, surprisingly enough, also for us, I guess, was yes. What you see here are the resistivity versus temperature curves. For lanthanum 438 in red, you can see, once again, highly insulating, transition at 105 Kelvin, then semiconducting. Praseodymium 438 in blue, metallic, all the way through, no signature of any transition whatsoever. In addition to that, what we find in the DFT calculations is also consistent with polarization-dependent X-ray absorption experiments too. So this looked great. We had found a material that it's a very, very close cuprate analog, in that it has a layer structure. It is very close to D9 filling. It has the involvement of a single bond of the x squared minus y squared character, and finally, metallicity at 1/3 hole doping as we wanted. Now, okay, this is good, but ideally you don't want to be finding a metal, I guess. You want to be finding a superconductor. So if you look back into the phase diagram, you might instantly recognize what you want to do next, that it's to now electron dope this material and explore this other side of the phase diagram and see what happens. And what we thought could be a plausible way of electron doping this material was doing so with a 4+ ion like cerium, and this had actually been done in the past in quite a few different cuprates. And at least on the theory side, what we wanted to do at first was more of a proof of principle calculation, I would say, that is to show if you were to go to the side of the phase diagram, will you find a mod insulating phase? And the reason for that is obvious. In cuprates, there is always been the question that a lot of the physics that you see is the physics of doping a mod insulator. So does that phase exist here? Now, the reason why I call that proof of principle calculation is because this entails a 25% substitution of praseodymium by cerium, which of course we know in the experiments may be pretty hard to achieve. But if you were to go all the way to D9, you will indeed find in a very natural way a spin 1/2 antiferromagnetic insulator analog of parent cuprates. And even though this answer may seem trivial, once I get to the 112 materials, you will see that it's not so trivial. So in that situation, if you look at cerium-doped praseodymium 438 and you go all the way to D9, This is the type of band structure that you will end up getting, in which you have a band gap opening up, and in which your nickel D unoccupied bands have x squared minus y squared character only, so that it's where holes would go if you were to now hole dope from here. You can calculate quite a few things, and one of the things that we looked into was the value of superexchange. We know that's a relevant parameter in the cuprates, and we actually get a value that it's very, very cuprate-like. So at the time, of course, this looked very promising to us, in that now we had analogies with cuprates at different D fillings, suggesting that intermediate cerium doping concentrations near 1/8 could be the appropriate place to search for superconductivity. However, reality strikes back. Experimentally, it turned out to be very, very difficult to dope this material. So this project was on hold for a while. But now, of course, the discovery of superconductivity in this other member of the series, in the 112s, brings hope to try to go back and try the doping of these materials a little harder. And who knows, maybe these 438s are the next superconducting member of the nickelate family, or at least that's the hope. Now, this brings me naturally, of course, into the second part of the story, that is what I now call the story of success, and that's the story of the 112 materials. So as I anticipated in the beginning, superconductivity has recently been found in hole-doped neodymium nickel oxygen 2, and given the previous part of the talk, you may now wonder why neodymium, why not lanthanum? Well, they actually did try lanthanum, as you can see here in the highlighted part, but strontium dope, lanthanum 112, keeps on being insulating. It's not superconducting. So they turned to the chemical pressure argument that worked for us in the 438 materials, tried a smaller ion like neodymium instead, and ta-da, neodymium did work. You may also wonder, okay, is then the story of this 112 material something new? Not really. The first report, at least that I've known of, on 112 materials goes all the way back to 1983, so even before the discovery of cuprates. So then why did it take so long to make this system superconducting? I believe it was probably a combination of reasons. Experimentally, when they looked at the magnetic and transport properties of these 112 materials, they turned out to be not very cuprate-like. There is no signature of long-range magnetic order, a D9 filling, and the transport shows weakly insulating or metallic behavior. Then theory came and determined that these 112 materials were also non-cuprate-like in terms of their electronic structure. And in addition to that, these systems are pretty hard to synthesize. It's in particular the reduction process that gets very tricky. So I believe this is what made people think, okay, this is not very promising, let me move on to something else. And by people, I mean ourselves, I guess. But of course, we now know that that's completely wrong, because strontium-doped neodymium 112, it's actually superconducting. So what you see here are the resistivity versus temperature curves of the parent phase in red and the doped phase in blue. So the parent phase, as you see, is metallic at high temperature, and then it has a low temperature upturn in the resistivity. The doped phase is also metallic, with the surprise of the superconducting transition, whose onset is at 15 Kelvin and zero resistance is reached at around 9.1. The observation of superconductivity is robust. What you see on the right are resistivity versus temperature curves of quite a few different samples in a zoomed-in temperature range, and you see that all of them have the resistivity drop. There are some differences between them that they think are actually due to either non-stoichiometries or to the crystallinity of the parent phase, actually. That's why, as I said before, these systems are pretty tricky to synthesize. Now, of course, this has created a lot of excitement, as you can tell by the amount of papers appearing on arXiv since August, and this list is already outdated. But what I would like to tell you today is what did we decide to do? And the question that we wanted to address is this material really that different from a cuprate, or is there something that we overlooked? And the way in which we wanted to address this question was by analyzing, using first principles calculations, different factors that seem to be relevant to set up TC in the cuprates and compare them to the nickelates. And the factors that we wanted to look into were the charge transfer energy, or the DP, energy splitting, and in cuprates at least, the smaller the splitting, the larger the TC. The easier it is, if you like, to form singlets. The second factor that we wanted to look into was the splitting between the two EG orbital energies, and at least in cuprates, the larger the splitting, the lower the mixing, and the higher the TC. And the last factor, which we actually believe is the crucial one, was the T prime over T ratio, or the ratio of longer range hopping to nearest neighbor hopping in a one-band model. And at least in cuprates, the larger this ratio, the larger the TC. Now, before I go into those factors, let me introduce you to the electronic structure of neodymium nickel oxygen 2 in comparison to its cuprate analog, that it's also superconducting upon doping, and that it's calcium copper O2. So as you see here, in both cases, you have a wide dx squared minus y squared band crossing the Fermi level. If you like, in that regard, they may not be that different, other than a reduction in bandwidth in the nickelate with respect to the cuprate. But when you look here, you instantly recognize a very important difference between these two materials, and that is where do the spacer cation bands appear. In the cuprate, the calcium 3D bands are well above the Fermi energy. They don't bother you much. In the nickelate case, you instantly see that that's not the case. You have neodymium 5D bands crossing the Fermi level, and they actually do so at different places. They cross at gamma, where they have mostly DC square character, and they also cross at A, where they have mostly DXY character. So in this regard, the cuprate and the nickelate, not so close. This difference is actually even more evident if you look at the corresponding Fermi surfaces. The bottom one is the one for the cuprate, where we have just this large, hole-like dx squared minus y squared Fermi surface. In the nickelate, you preserve that Fermi surface, but in addition to it, you have these neodymium d electron pockets that appear both at A, those are the red guys, and at gamma, which is the blue guy. So in the nickelate case, you start from a situation in which in the undoped compound, you have self-doping of the large hole-like Fermi surface due to these neodymium D electron bands, which we believe are the ones that are the origin of the experimentally found metallic behavior. Okay, so now that I've shown you at least some basics of the electronic structure, let me then move on to the three factors I mentioned I wanted to analyze. And the first factor, if you remember, was the charge transfer energy, or the DP energy splitting. So what you can see here on the right is the top, the same band structure that I showed you before for the cuprate, bottom for the nickelate, followed by the transition metal dx squared minus y squared states in red, the DC squared states in blue, and the oxygen px plus pz in green, and px plus py, sorry, in green, and the oxygen pz in orange. So already by eye, you can tell that in the cuprate case, the P and D states fall more or less at the same energy, whereas in the nickelate case, they are very far apart. Of course, you can be finer and calculate on-site energies to get a value out for this splitting. And if you do so, in the cuprate case, you end up finding a value of around 2 eV. In the nickelate case, you find double that value, somewhere around 4. So in this regard, once again, the cuprate and the nickelate, maybe not so close. Now, in cuprates, people have actually spent the time to correlate directly the value of TC with the value of this DP energy splitting, And that's what is shown in this graph, where different blue points actually represent different cuprates. The only thing that I want you to look into here is that the maximum value of the DP energy splitting that you can get in a cuprate is around 2.6 eV. So, of course, the nickelate value would be way out of the bounds of superconductivity, at least in the cuprate context. Whether this is telling us that perhaps this is a factor that is not that relevant for superconductivity, or maybe it's telling us that it is, and that's why here you only get a value of TC of 15 Kelvin, that's a very important question to be answered. I do not have an answer at this point. Okay, so I've shown you quite a few factors in which the cuprate and the nickelate seem to be different. Let me now show you a few in which they are much closer than we expected. The first one is the dx square minus y square and dc square splitting. As I mentioned, in cuprates, the larger the splitting, the larger the TC, basically due to the reduced mixing of these orbitals. This has to do with nesting, of course. And if you look at the value of this splitting for the cuprate and the nickelate, you find for both of them a value that it's practically identical. So in this regard, again, they are much closer than we expected. And finally, the ratio of T prime over T, or ratio of longer range hopping to nearest neighbor hopping in a one-band model, if you do tight binding fits to the dx square minus y square band, you find a value of this ratio that it's actually identical in the cuprate and the nickelate as well. So again, in this regard, they are much closer than one could expect. So what I think I can tell you at this point, at least about the parent phase, is that in spite of negative conclusions from earlier work, these 112 materials may actually not be as bad as we thought as cuprate analogs. Besides this larger DP energy splitting and the presence of 5D states near the Fermi energy in the parent compounds, all other electronic structure parameters seem to be favorable in the context of superconductivity as inferred from the cuprates. Now, I wanted to finish by telling you what we think it's left to do, and in some cases, or in some of the things that are left to do, electronic structure methods will probably have a lot to say. In the 112s, this is, of course, just the beginning. They tried whole doping with strontium. What about using different dopants that in cuprates also give rise to superconductivity? Will you find the same here? Why is the neodymium 112 material superconducting upon doping and not the lanthanum 1? Is it really a chemical pressure effect, or is it just growth conditions? Again, we don't know at the moment. Are there samples at optimal doping, or can TC actually be higher? We believe that due to the self-doping effect, TC could actually be higher here, but again, we don't know. Their experiments are performed in thin films. Is strain playing a role? They are under a bit of a compressive strain. Is that actually doing something? Again, we have no idea. And finally, they did try whole doping, but what about electron doping? In cuprates, in particular in 112s, this also gives rise to superconductivity. Can it give rise to superconductivity here as well? Again, we don't know. And that's just for the 112s, but then what about the other members of the series? I told you today about the n equals 3 members, which we believe are definitely worth to revisit because they are even closer to cuprates in terms of their electronic structure with respect to the 112s. And given that it's so hard to dope those materials, you will also have the possibility of going to higher order nickelates. It's like the 4-layer and the 5-layer material, because these two guys will give you direct access to the dome area of filling without even doping. And even though at the time we thought we wouldn't convince anybody to look into these materials, now Julia Mundy at Harvard has samples of these parent phases grown by MBE, so it's a matter of reducing them and see what happens. But of course, this is all work in progress. Hopefully, I can tell you much more about it very soon. But with this, I will just finish. I think I'm also over my time. Hopefully, I have been able to show you that these systems are interesting and that you can do a lot of things in order to address their electronic structure using first principles. And I will just leave you with a question, as I started with a question, that is, will these layer nickelates be the next iron-based superconductors, tying up to a research talk? And with this, I will just finish, and thank you for your attention.
Thank you very much. Thank you very much. Very interesting story. Very interesting. Questions?
I have a question on the superconductivity. So by looking at your band structures, I guess that, and there are many, I saw that in all these papers, there are surely people that have talked about the order parameter. It's going to be again a D wave. If this,
it's the x squared minus y squared. Yeah.
Now, the self-doping that you were showing, you said at some point that it's not clear what this self-doping is doing, but can you say a little bit more about this self-doping? So this, what you say that this this pocket that you have there, which comes from the neodymium, what do you expect that this is going to do, or this is doing to your system?
So, for example, I didn't show that, but in their paper they do have Hall data. The surprise was actually that when you look at the undoped and the doped material, the Hall completely changes sign. It's actually negative for the parent compound. And you can actually get a value that is very, very close to what they have if you consider only the neodymium D pockets, which is sort of telling you that then maybe the Hall-like Fermi surface is gapped out. Now, if you don't have magnetism, what is it gapping it out? Again, I don't know. What we are pretty much sure now is that when you dope the material, gradually the self-doping effect goes away. So the point is, even if the parent phase may have these differences with cuprates, some of them actually go away when you dope, and you make it more cuprate-like. At least that's the thought.
More questions?
Yeah, I have two questions about the phase diagram that you have shown. So first, which is the phase that you have at just about antiferromagnetic mode insulating phase? And also, what's the pseudo-gap phase?
The pseudo-gap phase, it's a phase in which you have the Fermi surface being gapped only at certain points, basically. That happens, though, at temperatures that are above TC, if you like, and it happens in the range of the underdoped compounds. So before you get to superconductivity, and basically as you lower the temperature, those Fermi arcs just go away, and that has been seen by ARPES, etc. But again, you have to consider what we are doing here is T0. So you know.
More questions? So if we don't have more questions, then we have a lunch break, and we have to thank the speaker again.
Okay. Before we go to lunch, we want to take a conference picture now, so we will ask you all to go to the stairs in the entrance of the building, so we'll take the picture right there now, and then we'll come back later at 3. Here.